So we have been talking about percentage concentrations for solutions. We talked about molarity and mole fraction in the previous videos. And if you look at molarity once again, what it gives you is moles per liters of solution. So it gives you the number of particles, of solute in a certain volume of the solution. and it so happens that there is a second sort of analogous uh, concentration unit that's called the molality. The molality, other than sounding quite familiar to us, like being molarity, uh, it's 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 quite different in its approach to calculating the concentration. So you still have the moles of solute in the numerator, but in the denominator you have kilograms, kgs of solvent. And let me write that in capital letters, kilograms of the solvent. So in almost all of the concentrations that we use, we take something of the solution in the denominator, but in molality we use kgs of solvent. So it figures out, this molality figures out number of particles of solute in in a mass, in certain mass of the solvent. So just like we did with the other concentration units, let's try solving a problem to find out the molality. So let's say you have a solution of C6H12O6, and it's just the familiar glucose, and you have a solution of glucose, 4.80 grams of glucose in 90 grams of H2O, or water, and you want to calculate the molality of the solution. So uh, for instance, I'm just writing out that the molar mass of C6H12O6 of glucose is 180 grams per mole. It's not strictly that, but we can take it for an okie dokie accuracy. So first let's figure out moles of C6H12O6, the moles of solute, and that would be 4.80 grams over 180 grams per mole. So you divide the actual mass by the molar mass, and that comes out to be, if you do the math, it comes out to be 0.0266 moles. And you now have to figure out the kgs of solvent, and notice it specifically says you have to only take kgs here, just like molarity said you have to take liters of solution. Here you have to take kgs of solvent. So in this case the solvent is water, so 90 grams of H2O, 90 grams of water, is the same thing as saying 0.09 kgs of H2O. So what I just did is, since one kilogram contains 1,000 grams, so 90 grams would be equal to 90 over 1,000 kilograms, and you get that. And if you plug that in, in the equation that we have in the concentration definition, the definition of molarity, you have the molarity to being equal to molality, the molality to be equal to 0.0266 moles divided by 0.09 kgs. And if you solve for that, which I don't expect it to do it by hand, but if you can, that's really great. This is equal to 0.296 moles per kgs. And just like just like for molarity, we had a unit that we called as molar. Molar. This was pronounced as molar, and it was moles per liter. We have a unit for molality as well, and it's represented by small m. It's called the molal. Molal. So instead of the r's, we're replacing the r's with the l's, and that's basically what the difference is. And in and it's equivalent to saying moles per kilogram. So 0.296 moles per kilogram or 0.296 molals. And so that's what the molality is. And I want to end of this series of calculating concentrations of solution by taking up parts per million. Parts per million. So let's say you have a very, very minute concentration of something within something. So a common example of a minute concentration, of a small concentration, is mercury, Hg, in water, in drinking water. So the water that we drink contains traces of Hg, and it's not so much that you could write up, let's say, molarity and molality and get an appreciable number. So instead of that, instead of taking molarity or molality, we take the ppm instead as parts per million. And so ppm is a mass to mass ratio. The ppm of a solute, or ppm of anything, is equal to the mass of the solute over total mass of the solution. And since we are taking it per million. So instead of multiplying it by 100 when you're doing percent, in doing percent you multiply it by 100. When you're doing parts per million, you are multiplying it by a million, 10 to the power 6. That's what the million is. So it's an analog of the mass percent. The mass percent, the m by m percent that we talked about in the first video, the very beginning. It's an analog of that, but for traces, for amounts that are really, really small. So for example, let's continue with the example of mercury in water. The permissible limits in most countries is 5 times 10 to the power minus 7 grams. 5 times 10 to the power minus 7 grams Hg in 1 gram of water. And this is like the permissible limit for Hg in drinking water. Permissible limit. So if you want to express this concentration in parts per million, you would just write it out. So 5 times 10 to the power minus 7 grams on the top, and since the total mass of the solution would be the entire solution of drinking water would be 1 gram. That's the sample that we are given with. You multiply that by 10 to the power 6. So the ppm in this case would be 0.5. And there is also parts per billion, parts per trillion, and that would just mean so if you, instead of having parts per million, you have parts per billion. In that case, instead of having a million here, you write a billion. So 10 to the power 6 becomes 10 to the power 9. If you have a trillion written there, 10 to the power 9 changes into being 10 to the power 12. And you can do so on and so forth. And usually ppm is kind of the standard of taking trace concentrations in traces, but it's not something that's the convention. You can take any type of parts per billion, trillion, thousand if you want, and it would still make a lot of sense. We also have not considered normality yet. Now normality is something, I'll just write the brief definition of it. Normality is equal to number of equivalents of solute over liters of solution. And the number of equivalents is a rather big term, and there are a lot of ways to calculate this number of equivalents. The normality being a very useful unit for performing titration reactions and other things in laboratory chemistry is still used. However, the concept the concept of equivalence that deserves some separate videos on it of its own, and normality will be considered as a part of that series on the concept of equivalence. So I hope that this video mini series on calculating concentrations of solution has been helpful, and we'll continue talking about solutions and chemistry in general in the next ones.